Okay, so this video is an introduction to the very nice theory of Heyting algebras and how this relates to the kind of sub-objects that we consider in topos theory. Okay, um, so one of the main ideas is that we can take an object in a topos and we can form a kind of, well, we can consider all of the sub-objects of that object and we can form a kind of category, a certain kind of pre-order. In fact, it's a certain kind of partially ordered set. In fact, it's a lattice. In fact, it's a Heyting algebra. And basically the idea is the objects there are monics, and let's say sub-objects of our object A, and we draw an arrow from a sub-object L to a sub-object R, if and only if L is contained in R. And we normally write this L less than or equal to R, okay? And there's various operations in this, including the ideas of meets and joins. And the first thing in these pictures red, I'm trying to illustrate that this reminds me of a book I read on projective geometry by Lawrence Edwards, and he begins by talking about three-dimensional projective space and how by doing these meet and join operations on lines and planes you can and points, you can make the other kinds of figures. And it occurred to me that, you know, in this topos of, if we take this topos of smooth spaces, we can define these flatter spaces as things that have constant gradients, because gradient's well defined using this infinitesimal object and such. And then you can view all those things as sort of sub-objects of R cubed, and you can really reframe his whole discussion in terms of this kind of algebra of sub-objects, which we're going to talk about. So there's lots of things to say, and it's extremely interesting, actually. This really, in my opinion, gives a much easier to think about and more kind of holistic view of the algebra of, well, of topos logic, basically, and also applies beyond that. So it's very cool. So firstly, a pre-order is a category where there's at most one arrow from one object to another. Okay, and when there's an arrow from X to Y, we don't have to label it because there's only one. And we normally write that there's an arrow from X to Y by writing X less than or equal to Y. A supremum of a pre-order is a terminal object, because for any object, so if we call the supremum 1, then for any object alpha, we have alpha is less than or equal to 1, because there's one arrow from alpha to 1. Similarly, infimum is the initial object. The greatest lower bound, also called the meet, denoted X wedge y is just the categorical product of x and y. We see why it's called the greatest lower bound, because it has the property that x times y is less than or equal to x and it's less than or equal to y, and if s is also less than or equal to x and less than or equal to y, then s is less than or equal to x times y. The least upper bound, also known as the join or x vy, is the coproduct x plus y. Since there are no parallel arrows, equalizers and co-equalizers trivially exist for these pre-orders. Also, in a pre-order, an exponential object, like y to the power of x, is a material implicate. So we usually denote that as x implies y, and it's such that for any s, we have that s is less than or equal to x implies y, if and only if x times y is less than or equal to y. So we see some of the kind of intuition about this here. You see, these are basically just two ways to write the same thing. This way on the right looks very familiar because it's exactly what exponential is, this property of doing the exponential adjoint, the transpose on arrows in a pre-order. On the left, this is basically the result about what implies means in terms of topos logic. And it's basically saying that to say that S is contained in the stuff where x implies y, is shaded in this orange here, is equivalent to saying that x and s is contained in y, as you can see by this little green sub-object I've shown here. Okay, so right, let's carry on. A poset, or a partially ordered set, is a pre-order where we don't have arrows going in opposite directions between a pair of objects. So more precisely, for any pair of distinct objects x and y, we don't have that there's an arrow from x to y and an arrow from y to x. Okay, a lattice is a partially ordered set with products, co-products, initial and terminal objects. I guess in that case of a lattice, that the co-limit of a diagram is just the limit or co-limit of a diagram is just the product or co-product of all the objects within that diagram. Anyway, a Heyting algebra is a Cartesian closed lattice. So basically, it is a partially ordered set which has products, co-products, initial object, terminal object, and exponential objects. Okay, now Like Heyting algebras are very cool because we can define these different things. And if you haven't already guessed, well, let me just get to the main result and then I can talk about the implications. So, other thing I need to define is slice slice category. So for a topos E, let's let E slice A be the category which has as objects arrows from arrows into A, and as so the objects of E slice A are arrows into A, and the arrows of E slice A are arrows like K from B to C, arrows between objects in E essentially, but such that, for example, K would be considered to be an arrow from F to G in this slice category, if and only if this diagram commutes in E. So we have K after G after K equals F, where we can think of, at least in the category E, we can think of K corresponding to this arrow from B to C. Now we let sub A denote the full subcategory of E slice A on the objects which are monics. Okay, so basically this category, which is our main thing of interest, the objects here are monics, or we could say equivalence classes of monics, and then we'll do an arrow from a monic X of A to a monic Y of A, if and only if X is contained in Y. So that means there exists a monic K such that Y after K equals X, okay? Now we can define this more precisely. We can actually think of the objects as the classifying arrows of a monic, so we don't have this issue about worrying about distinctness of the because there can be many kind of equivalent monics. Anyway, now the point is that sub A is a Heyting algebra. Okay, so this is extremely deep. So what's it mean? Well, basically, the idea is that this AND operation, which we've been talking about, is exactly so the AND operation in sub A is exactly this. It's exactly the product operation. Sorry, I mean the AND operation of monics the AND operation of subobjects of A corresponds exactly to the product operation in sub A. The OR operation of subobjects of A corresponds exactly to the coproduct in sub A. The terminal object of sub A corresponds exactly to the full subobject of A. The infernum of sub A, the initial object of sub A, corresponds exactly to the false or empty subobject of A. The exponential object of sub A corresponds exactly to this implicate thing, x double arrow y, which is like this subobject shown in orange here, at least in the category of sets. Not x in terms of the kind of operation involving subobjects can be thought of as x double arrow 0 and so on. So this is extremely deep. We can basically think of all this logic as going on in this kind of context. Now, there's various other things. So one of them is that there's another way, like a closely related idea, is this idea of this power object, omega to the power of A, which is actually, it's also a Heyting algebra, because basically we can talk about the same kind of thing all these subobjects of A from this context, and which is included in which. But this context is actually a complete Heyting algebra, in the sense that every family of objects in it has a least upper bound, and it's related to the idea of a locale. Now, this is another very lovely idea, which is basically like going back to this discussion of sub A as a Heyting algebra. So if we have any arrow in our original category, let's say our topos E, then we have that if we have an arrow F from A to B, then we can form this contravariant functor f to the minus 1. Well, no, sorry, we inform this functor, it's not contravariant, we inform this functor f to the minus 1, which is a functor from, it's a covariant functor actually, and it's functor from sub B to sub A. And what it does is it takes say a monic in B, let's say little b, and it outputs the pullback of B along F. And since the arrows aren't labelled in sub B and sub A, we don't have to say too much about them. Suffice to say, it preserves containment. In fact, this type of functor preserves all of these kind of Heyting algebra operations. Now, there's an interesting kind of way we can use this to actually form a contravariant functor from our topos E to set, where basically we send every object of A to sub A, and we send every object A of E to sub A, and we send every arrow F from A to B in E to this F to the minus 1 functor, and that is this is a contravariant functor. This capital F1 here. Anyway, that's all the major stuff said. One thing I wanted to say is that all this stuff about Heyting algebras and how this stuff from sub A and so on, well, that stuff, the way it's described, it basically looks like the Curry-Howard-Lambic correspondence. For example, 1 corresponds to true, corresponds to the terminal object, etc., etc. Product corresponds with and intersection, and all these different things. We see this connection really happen closely with the Heyting algebras. Now, there's various other sort of remarks I have. There is such a thing as a bi-Heyting algebra, where it's possible to define subtraction, and that's probably useful for my graph problem. We know there's this interesting way of representing the material implicate, the implies arrow. How do we say stuff like y to the power of f or f to the power of x? What's eval related to this exponential object? What about for example, we know that OR goes from omega times omega to omega, so OR to the power of A ought to go from omega to the power of A times omega to the power of A to omega to the power of A. Now, is that a functor? Can that be represented as a functor, which somehow takes a couple of sub-objects and gives another one? We know that for example, we have this functor sigma A, which lifts us from objects of sub A to the domains of harmonics in C. So how does that work? And also there's the one the other way around, which should be A star. How does the coproduct correspond to the union in this Heyting algebra correspondence thing? And can this functor here be extended so that it can be considered a functor from E slice B to E slice A. And I mean, we don't necessarily have to work in a topos to do a lot of this stuff. We can define sub A for any object in any category. It's just that some of these functors might become pseudo functors. So there's certainly a lot to look at with this stuff. And I suppose one of the main things I want to do is to understand exactly how sub A corresponds to a Heyting algebra. And also there's various other things. Johnston and McLean talk about f to the -1 amongst this family of kind of functors, I think including stuff like f star and sigma f and different ones, which go between E and E slice A, and they're related to stuff like exists and for all, and there's loads of adjunctions everywhere. And I think if I can understand that relationship, then I'll really understand the sort of one of the most important things in all this topos theory. But I mean, the real nice picture from all of this basically is that there's this lovely sort of lattice of inclusion for every object in every category, and then these arrows are sort of translating these lattices, sort of moving the bits and pieces in one to the bits and pieces in another in a very pleasant way.